So today's plan is to look at the linear classifiers first. So linear classifiers are very simple classifiers, but still uh, it can give a lot of insight about image classification. We will look at linear classifiers well and then understand what gradient descent means. And then we'll briefly write a gradient descent code. And then we will write it in PyTorch and understand what automatic gradient computation is. And our plan is to implement a linear classifier in PyTorch. And then we will start looking at hopefully the convolutional neural network. So now, uh, if you think about this parametric approach of classification, now think about an image like this, a 32 by 32 by 3 image. So you can see that this 3 is to represent the colors in that image. The color, it's a color image of a size 32 by 32. It's an image of a beautiful dog. And we can see the total number of pixels there is 3072. How do we get that? 32 times 32 times 3. Total number of pixels is 32 times 32, but because there are 3 colors, you will have 3072 numbers when you multiply 32 by 32 by 3. Okay. So what we will do is we feed this dog's image to a certain function that takes the image itself and then it is parameterized by its weights, W. So parameters or weights, we call them, these Ws. And now its task is to output 10 numbers. Why 10 numbers? We consider this as a 10 class classification problem where the class names can be cat, dog, deer, bird, so on, car, truck. Here, obviously, we want the dog score to be high and the dog class to be picked because it is a dog. Yes. Uh, Give me a minute. Yes. So now you can see the sizes of this, right? Now, because our image of small x is a 3072 dimensional quantity, and we have to produce an output of a 10-dimensional quantity. That means for the 10 classes, each class will have to have a score. This W matrix must be 10 times 3072. And for each of these classes, we need to have a so-called bias of 10 dimensions. So I hope you can understand that when you multiply this 10 times 3072, right? 72 matrix, yeah, this one, with this image of 3072, what is resulting is a 10-dimensional quantity, right? And therefore, you can add a 10-dimensional quantity to that. This is what this shows. So I hope it is clear to you. So we'll do exactly something like this using Python today. Yeah. Now, I will pictorially represent this and show you different pictorial views of this. These slides have been inspired from Justin Johnson's slides. Now take an image like this. Now let's not consider that this image has 3072 pixels. Let's consider for the time being that this image can be represented using 4 numbers. These are the 4 numbers. And this is called the algebraic point of view, explaining the previous equation that I showed you. Each of these rows represents the weights for each of the classes. This is a 10 class case. So you can consider that this as the cats, the 3 classes, cat, dog, and sheep or something. And this corresponds to another class, and this corresponds to another class. And of course, these are the biases. You can see them. So you can see this row multiplies this row, and you get one single number because of that inner product. And then you add this 1.2 to that to get this number. Again, you can see the dimensions. So it's a 2 by 2 one, and this is a 3 by 4 vector. Each of them is a 3 by 4 vector. So therefore, because you have 3 of them, it's a 3 by 4 matrix. and this is a 4 vector, and then you have 3 numbers here in the bias, and output is a 3-number output to represent the 3 classes. So uh, what we do here is stretch each pixel into a column, right? Stretch each pixel, stretch the pixels into a column like so, and then we multiply them. So maybe to encompass the bias, you can join that bias column also into this if you wish, and put a 1 there. So an extra 1 to data vector bias is absorbed into the last column of the weights matrix to produce a score for each class. Yeah. So now predictions in this case are linear. What does that mean? In this case, you can see it is a matrix vector multiplication. This kind of a multiplication, if you consider the bias also, you can see it's a linear operation. It's a linear operation, especially when you put this bias also into this vector. So in other words, if you get a score like that, and assume that you make this image darkened by multiplying by 0.5. Now it produces the scores and multiplied by 0.5. So that is the meaning of being linear, but then it will produce the same classification answer because the maximum value will be for the same class. But unfortunately, the scores depend based on the uh, images values. So this is some kind of a problem. You can see mathematically, we can express like this. If you multiply x with c, we have WCX, and the classification scores are multiplied by C. Okay. Is there a question regarding that? Okay. Now, why are these scores not correct? For example, if we consider this as the cat class, this as the dog class, and this as the sheep class, you can see the dog class is the highest. It is not correct. Why is it not correct? Because we have not yet trained this W matrix. It has not been trained. So when we train it, these scores will hopefully be correct. How do you train it? We train it using this mechanism called gradient descent. So now we are going to understand this gradient descent for a single variable. In this case, this is a 5-dimensional problem. You can see there are 5 numbers here. It's a 5-dimensional problem in this case. But we will understand just a single dimensional case and try to do some gradient descent and understand how exactly that works. Yeah. I hope there are no questions up to now. If you have a question, as usual, you can just turn on the mic and ask that, or you can just type a question and I'll be very happy to answer. Please don't hesitate to ask. Yes. Okay. So now this is our function, and consider that as fw. It's a function of w. I will not write my x here. Consider this as fw. Okay. So now you can see this is my w axis. What I want to do is start with some initial w. Let me start with some initial w. I will take some value like this one. Assume that I start with W naught equals, let's say, 0.9. W naught equals 0.9. That's what I'm going to start with. So what is the value of the function at W naught? So value of the function is something, right? This is the value of the function at W naught. Yeah. What is the updating rule for this? The updating rule is, now think about that you are in a mountain top. Now, similarly, here is also you are in a mountain top or something, and you want to climb down the mountain. If you want to climb down the mountain, the best thing that you can do is move in the direction of the highest slope. Highest slope. So this is a one-dimensional problem. So your highest slope has only two directions. Either you can move this way or you can move that way. Only two directions. But if you are on a real mountain, actual real mountain, then you have a choice, right? Now you here in this mountain, if you are somewhere here, okay, you can move in all 360 directions. Now, if I get a plan, so you can move this way, you can move that way, you can move this way, you can move in all 360 directions in this case, because it is a two-dimensional problem. Because this is a one-dimensional problem, you have only two choices: move left or move right. Let me ask you a question. In this current situation right now that we have drawn, in what direction should you move to reach the minimum? To reach the bottom, reach a minimum, should you left or right? So please type L or R to see whether you are comprehending what I'm trying to say. Okay, carefully observe where you are. Carefully observe. Uh, I said a minimum. So that means we have to move to the closest minimum. Closest minimum, yes. Now some people have changed the answer. Yes, I should have been more specific about that. Yes, a lot of people are writing the correct answer. Yes, we have to reach the closest minimum. That closest minimum is actually the minimum over here, this minimum. That's what we need to reach, right? To reach that minimum. And um, that means this is the correct direction to move. That, thank you very much for your answers. We are to move in the right direction. Now, how can you mathematically specify that right direction? You have to move along the slope, move along the direction of the slope. How can you define the slope? Slope is the gradient, right? Slope is the gradient. Now let's draw the gradients here in this course. So I'm going to draw a few lines to show the gradient. Gradient is the tangent to this, right? Here's the gradient. So of course, in this case, uh, uh, you compute the gradient as this slope is, you can see that gradient is negative, right? Negative. So you know from O-level mathematics that if you have a function like that, the gradient is positive, right? Positive gradient, right? Line like that. If you have a line like this, gradient is negative, right? That is our understanding. So actually what you do, you get this theta and consider tan theta, right? Tan theta. So here tan theta is positive. In this case, this is a large angle, so tan theta is negative. And theta is negative in this case. Right. So this is a negative gradient. Okay, I will draw the gradient somewhere here. That's also negative, you can see. Right here also the gradient is negative. One more. Here also gradient negative. One more. Gradient is low but negative here. Right. You can see at all these places the gradient is negative. So if the gradient is negative, opposite direction of negative is positive. That's why we are moving in the positive direction. So therefore, the rule of reaching the minimum is moving in the opposite direction of the gradient, negative direction of the gradient. When the gradient is negative, move in the positive direction. When the gradient is positive, move in the negative direction. Therefore, I should write a rule. Our rule must be W, I will write T plus 1 to something, T plus 1, next W must be equal to current W, WT, right, minus, minus, may I write F prime for the gradient, F prime, at that W, WT, That's a gradient, negative direction gradient. It is some steps then. That's the equation using which we can do gradient descent. So you can see this we call the learning rate, LR, learning rate, right? This is the gradient of the function. So can you see that? So if you apply this rule, so you go to one more place. Let's say you moved and you went there, and say the W1 here, W1, maybe it is about 1.7, and you estimate the gradient here, and again the gradient is negative, so you move in this direction. Again you move to a point, maybe you're at 2, again the gradient is negative, you move again, and maybe you reach here. Again, the gradient is negative. Maybe you go like that. So slowly and slowly, you may reach the minimum. Of course, you can jump over the minimum. That kind of thing happens. But this is the gradient descent. Okay. Is there any question about this? So are we okay for this gradient descent? But now consider now if you mm, start somewhere here. Let's say you start at 0 something exactly somewhere here. Then you think about the gradient. Here the gradient is positive, right? And then that means you have to move in this direction. Assume that you move here. Okay, how much you move, that you have to decide. That's a step sign. Again, consider the gradient. Gradient is still positive, and you move in that direction again. Gradient is still positive. Even here it's positive. You move again. Can you see that? So with this rule, you will reach the minimum that is closest to you. Okay. So now to show you again, if you do run this in the computer, what happened? This is the W naught, the starting point. So I think I have selected point 2 or something as a starting point. When I write the code, you will see that. So this I selected point 2 as W naught, point 2. And then when you do that gradient descent, you see, hopefully you will reach the minimum, but there is no guarantee that you will reach the minimum, a minimum close by. So this is gradient descent. So now our task is to implement that in on our computer, and we will do that first of all using NumPy, using our own understanding that we got right now, and then we will do it in PyTorch and using this autograd mechanism of PyTorch where the gradients are automatically computed. First of all, we will compute the gradient manually. All right. So now this one is that function. So this is the function. This function I wrote myself because it's a very nice function like this one. I manually hand coded that function. So may I ask what is the gradient of that function? Tell me what is the gradient of that function. Um, uh, we call it f prime w, right? F w is given. What is f prime w? Yeah. What is the rule for this? So our rule is we know that d by dx of xn, yeah, xn is equal, n is constant, n x n minus 1, right? So you can see I had to use my knowledge about computing derivatives to do this. Minus 1. So what is the derivative here? You get 4 w to the power of 3. What will you get here? 3 w to the power of 2. Yeah. So can you please do this? What's the next term? Yeah, okay. Some people are typing. I'm very happy about this and I'm very thankful. This is correct. So 2 times 12, you'll get 24. It will be minus 24 W. and plus 15 and 5, the derivative of 5 is 0. Okay, thank you very much. This is correct. And now we have to remember both these formulas, and using them we are going to implement. Any question before we start our Python work? Okay. So I will not show you the code first, but before we will do the Python directly. Okay. So first example in this case is this is our gradient descent. Using manually coded gradient, manually computed. For a 1D function. Yes, that's the thing that we are going to do. All right, so import numpy as np, and let's import MATLAB also, matplotlib. Yeah, so let's see where my kernel is working. Okay, so now let's call define def fw is return w to the power of 4 minus w to the power of 3 minus mm, forgot minus 12 doubling squared minus 12 times w squared plus 15 times w plus 5, right? That's our function. Return. All right. W. If you like, you can do plot this also. ELT show. ELT. Is that how you plot it? Okay, let's define the W before that. The W, let's call the W's. Linear spaced numbers from, let's say, -4 to 4 or something. Yeah, okay. So let's do this. So you can see the function that we have. This is what we own, right? Yeah. Yes. Okay, so we need the gradient now. So if we call def dfw, so that's the gradient. So it is doing that. Yeah, so it is good. So then we move that. So now to do the gradient descent, we need a W node. W node we get as 0.2. Then for I in range, let's do it about 10 times. 10 times W is actually W node is 0.2, and we said W equals W node, right? W is our update rule, W minus eta times dw. So we have defined what eta is, our learning rate. Let's say it's 0.2. Okay. So now we have to do a plotting also. Plot w with red. This also we can plot this dot plt dot plot. This will plot as a blue dot. Yeah. And then yeah. So now plt dot w. Yeah. We can show. Okay, this is good. So you can see that what we this is what we exactly what we want to do. Hopefully, it will reach some minimum. Yeah. So return result too large because around that W's are small, right? -4 to 400. Uh, dot W. The C number is good, right? I didn't get such a large number. Doesn't get too much. Oh, it has. I would reduce. I will keep W as 0.2. No, it's okay, right? So I had a too large a learning rate. So now you can see going down. So there's no guarantee that it will reach the minimum. So for example, if you have a very small learning rate like 0.002, it will move very slowly. So it will not reach the minimum. So if you have too much of a learning rate, you already solve the problem. Let's say 0.5 or something, I think it'll jump. See, it's jumping. So jump to the other side. So these kind of things happen in a gradient descent. So you have to have do other things. But right now it's okay to understand the learning, the gradient descent. Uh, So this is what it is. Okay. So maybe we can print this doubling, right? So print iteration W. Yeah. So what happened? You can see finally W has turned out to be minus 0.24. Yeah. If you differentiate and find, you get that kind of number. So I give you a few 1 or 2 minutes to do this on your own. Uh, but you can understand that there's only one important equation of this one, the gradient descent equation. I'll send this code to the chat also if you want to get that quickly running. But this is not exactly what we want to do. We want to just understand what gradient descent means. Now we want to do it using PyTorch. I hope you have installed PyTorch. Okay. Then let's go for the next one. Next one is gradient descent using manually computed gradient for 1D function using PyTorch. So why PyTorch? Because we want to use PyTorch for our neural networks data. That's why we want to do this in PyTorch. And I want to show you this concept of AutoGrad, automatic gradient computation. So when you want to install PyTorch, what you do is you search for PyTorch and you go to the PyTorch website. PyTorch is by Facebook, and you can go to get started. And then there are some switches that you have to pick. So stable, this is what you need to pick, and Windows, if your machine is Windows, and pip, as we have used environment pip environment big pig. Then you can see language is Python, of course, and then the CUDA version that you have. If you have a GPU card, you can pick. Otherwise, you can pick the CPU, and then it will give you the code to run. Yeah, code to run. Um, See, it slightly changes based on the choice that you make here. Can you see that? Yeah, it's changing. Yeah. So the code that you need to run. I hope you ran that. I think I mentioned that last time. Ask you to run PyTorch. So if you have not, please do this now. Go to your environment. You know that we have created an environment. I hope you did that. So I activate. You can do it using Visual Studio Code itself, but that's okay. Now you can see because I see CV here, I have that. So then you copy the command, this command, and you can paste it there. And run this. Run that. I will not do that because I already have PyTorch. Okay. So now let's do this coding in PyTorch. But for that, I can use exactly almost the same thing. So because I will be just manually doing the computations, but we just change into PyTorch. So I will not use NumPy anymore. I will say import torch. Import torch. Then I have to X, this W, I will define as torch linspace, not torch. Linear space from -4 to 4. And when you're plotting, you have to say dot to NumPy. So convert to NumPy and plot it. NumPy. Also this one to NumPy and do it. So that means you need NumPy if you want to, because you want to plot it. Okay, that's that. Lot. Uh, then the initial x value, initial w value, I will directly define it as a torch, a tensor w equals a torch dot tensor to, and require grad is not true. So I will not require grad because I'm going to manually compute the gradient. Okay. So now to plot, I have to plot it. I have to dot x items because these are tensors, and here w also we can compute the item. We not so up to now. Let's see whether this is working. Yeah, it's working. So now let's write the follow. So I in range 10, that's fine. Now gradient descent. mm, uh, Only the plotting code changes. Plot W dot item. So this is the same thing, exactly the same thing. So yeah, okay. So you got exactly the same number, and this is fine. One thing I forgot to show you is that if you just initialize this as not 0.2, but as we did initially, maybe you initialize it like 0.8, somewhere here, it will go to the next minimum, right? Let's do that also. Initialize that as 0.8. Initial value matters. If you initialize so, it will go to the other minimum, which is like 2.6 or something, I think 2.5. Yeah, 2.5. Yeah, 0.2. Okay. So you can see just what I just wanted to convert these variables to tensors. So and do this. Uh, any questions about this? This one is just for plotting, huh? Nothing important there. So it's okay. I will send that also in the group chat. Now, what is important here is we have said required at false. What does that mean? So when you say now W is the so-called variable that the sort of the first variable that we have, right? So if we consider this f as the final value, fx as the final value, if w as the final value, w is the sort of input that is the leaf, sort of the leaf node. So those, if we say require grad true, PyTorch, the TensorFlow will compute the gradients. So we will not need this gradient computing function. Remember now, this is a very simple one-dimensional function that I have. But for complicated neural networks, we cannot manually write the gradient expression. If you have to do that, you definitely this science would not have been happening. So because of this automatic gradient computation, everything is possible now for us in the deep learning area. All right. So now this is what we are going to do. Next exercise is using AutoGrad. Uh, Function using PyTorch, manually computed gradient using AutoGrad. AutoGrad. Okay. Is that clear for you? What we are trying to do? Yeah, I hope it is. So now I will get the same thing. Maybe I will write. I will copy this part and start writing. Okay. Okay. All right. Because we are using AutoGrad, we don't need the gradient function. So plotting part, it's okay. We can this is just for the plotting now, so we can use that. But eta we need, and W as a tensor we need. Uh, okay, let me copy this also. Okay, so this we plot the graph, and then plot this point also with blue, and eta has been defined. But now, what is the important thing here is required. I'm going to write it's true. Really required true. Okay. Now, in these cases, so let's write the for loop now. For in range 10. We just uh, write, compute this forward pass, loss or something, FW, that's all. So we compute the loss, FW, and then we will have the backward pass. And only thing that we have to do is take this loss and say loss backward. That's all. Then we can, already the gradients are there, we can use them, and then we can update the weights. Yeah, update the weights. And we are the weight updating part, we do it using no grad. So this is now you can see the important thing that I'm using here, w dot grad. So gradients of the loss function with respect to w is available here. Gradient of the loss with respect to w is available here. Actually, gradient of f in this case, loss function is f, right? With respect to w is available here. This is the important that you need to do. Exactly, you have to write it like that without creating a new variable. You have to write w minus equals. You cannot write w equals w minus. Okay. Then we zero the gradients. For the next one, we need to zero the gradients. Then we can plot with the red dots and print this. Yeah, that's all, I think. On the plotting, yeah, that's all. At the space here. Okay. So we can see we can do exactly the same thing, but now you can see there is no gradient computation manually. Yeah. So please observe this. We said require grad true. Therefore, when you say require grad true, with respect to that variable, with respect to w, the final losses gradients are computed. Any questions about this? Okay. Now next task is for us to use this concept and then use the writer linear classifier for those images. But for the exact images right now, unfortunately, we cannot do that because the CFA10 dataset cannot be downloaded right now due to a problem in the University of Toronto servers because this dataset is from University of Toronto. Let me try once to see whether this uh, can be done. Otherwise, we will use some other dataset. This dataset is called CFA10, right? That no, unfortunately, the University of Toronto servers are not working. Uh, Download, so we will use MList. That's okay. Um, so now this one is slightly cumbersome because we have to get the data set also done. So this is that right now what we are doing is linear classifier for MList we cannot download for CFA10 we cannot download MList. Okay, linear classifier for MList. Okay, little bit of cumbersome code to get the data working. Uh, import torch, import torch vision, import torch vision transforms as transforms. So these two, just to transform the data. So let's define a transform equals transform dot compose, transform to tensor. I want to do this normalize. Name to mean 0.5, transform normalize mean 0.5 and the standard deviation 0.5. Yes. So now we can download the train set of the data set like this. Train set, torch vision, dataset MNIST. So we will download it to this folder. We create a folder called data here, a data folder, and this is the training set that we are downloading. We have download and we applying the transformation. And then the train, we have to define this train loader by getting train set, and our batch size is 50. So let me define the batch size here. I will talk about the batch size a little bit later. So how many images do we feed to the network at the same time? That's a batch size. Some of these things are not too important to know now. And then the test data set, okay, exactly the same. But we have train false, so that's a test set. So class names, these are the class names. Yeah, this is the downloading part, and please write this and run. So it will download for you. For me, I think it's already in my computer, so it will not download. In your case, it will download the, oh, it is downloading the English data set. Okay, so I will give it to you so that you can run this code. So, okay, MNIST has been downloaded. So you can see it has created a data folder and it is in compressed form. It's downloaded. Then let's do the other part. Actually, we can plot some of these data points. So import mat. Yeah, I would plot some of these data points. Import numpy. Um, so I define imshow function. So what I'm going to do is take an image. Okay, you divide it by pi and point to pi to unnormalize, and then convert to a numpy image, and then showing. So that's okay, not too much of a function. And then so we do that using the so-called iterators because we have defined this train loaders and so on. Data iter is iter train loader, and then images and labels. So it knows all these codes because everyone has written these things. Uh, um, um, labels, next data iter, and im show that using that function that we have, and we can print it. Okay. Yeah, you can see these are the sort of images randomly taken, I think, because we have the shuffle, and you can see some of these images. These are these handwritten characters that we are going to classify. So to this one, we have to say 3. For this one, we have to say 2. For this one, I don't know. For this one, we have to say 5, and so on. That's the task that we are going to do. So it's a 10 class classification problem. And each of these data points is 28 by 28. You can see it's 28 by 28, right? So that's the number of numbers that are there in that. 784. It's a 784 dimensional problem. So here what we handled was a one-dimensional problem. This is a 784 dimensional problem. So the gradient descent has to happen in 784 dimensions. And definitely you cannot write uh, the the gradient descent computation by hand. Okay, so that is what we are going to do now. Let me import all these things again. I don't have to import torch so that it is a self-contained code. Torch and import import torch dot nn as nn. So the neural networks torch. Neural networks module. Torch vision we can import, and we can import the transforms, and I think it's enough matplotlib. We need, if we need, we can import. And so define the number of parameters. So I will call it as input dimensions, D in or something. D in input dimensions. It's a 28 by 28. What's the reason? Because it is these image sizes are 28 by 28. Number of classes. Um, K is equal to 10. This is the number of classes. Number of classes. This is the image dimension. input dimension, 28 by 28 pixels. All right. So then I will for this initialization of weights will standard deviation is defined as TD point very small number 1e minus 5 or something very small number to define this weight. So now I'm going to define our W and B. So remember in this case what we are doing is um, this one is what we are doing. So we need the W and we need the B. So remember that now it is not 3072 but it is 784 because it is 20 times 28 dimensional. Number of classes is 10. That's correct. So our W must be 10 times 768, that thing, 28 by 28. So 28 by 28 is, let me not make a mistake there. Hmm. Yeah, sorry about that. Not remembering that. 28 times 28 is 784 dimensions. So this is 784. Okay. So what should be the size of W? Okay, we can write it in different ways, but not exactly according to the slides. W equals dot random numbers d in times k and multiply by the standard deviation also. B we can initialize to zeros, 10 zeros. So you can see the slightly different way because I did not define as 10 times 3072, but 3072 times 10. That's okay, but you can see we can manage with that, right? Okay, so they have a defined. So epoch, how many times that we run it, we call them epochs, right? We can say maybe 10. And then learning rate, eta is 0.01 or something. Not something, it's very important. So because I know it works, I have selected that. And loss history, I want to keep the loss history. It's like that. So, all right. So now for each epoch, so let's see what we want to do. So what we do is we want to extract a batch of data from the using the train loader. We will extract a batch of data, and then we will do the forward pass, and we'll do the backward pass. That's all we need to do. And yeah, let's go about doing that. So you can see now for images labels in enumerate train loader. So you can see about everything. I don't want to write everything. I will type it now. So because we want to go slowly here. Comma. So we get images and data. Images and labels. Images and label in enumerate train loader. Train loader. Okay. Train loader. So in that one, we have to write the running loss. There a mistake here. Running loss is 0. Now, um, running loss we have to keep off. Okay. Okay. Road is there a mistake here? That's okay. Mm. Then we from the data we can get the input and label, HL label. Data extract from here, input labels. When I'm tempted to hit tab key and it enters everything, but I want to go slowly. Okay, we extracted the inputs, that's images. So that's images, batch of images. Okay, 50 images. Okay, and images. So we will leave them as 28 by 28 and flatten the images. So 28 by 28 vectors. Mhm. Right. So whatever the dimension. Mm. So you can write Dean also here. Let's do that later. Uh, so so I will call this X-train now for that batch. And from the labels, I have to create the so-called one-bit hot encoded ones, encoded labels. So Y train, torch zeros, labels dot size and K. That's okay. So and then for the correct one, uh, I put one. Yeah, yeah. Okay. So now my data is complete. One not encoding the labels is correct. So I hope you understand that. But if my label is 9, I put the ninth entry of a string of zeros as 1, like that. That's what I want to do. Okay. Then the forward pass, forward pass. So what should be the forward pass? My forward pass is easy. This equation Wx plus b. So forward pass score is x train times W plus B, or I can use the matrix multiplication. I will use the matrix multiplication x train dot mmw scores. Uh, is the train loader okay? It's correct. That's a forward pass. Now I computed the scores. Then I have to maybe I will not just call them scores. I will call them predicted y values, y trend, right? Is much more clear, right? Predicted y values. Then I need to compute the loss. Mean square loss. Squared loss. So loss is y pred minus y train squared mean. That's okay, right? So this is correct. Okay. Then the loss is there. So we can append that to the loss history. Running loss is yeah, okay. Loss history. History append, that's also okay. Yeah. Then now I want to do the backward pass. I want to backward pass. In the backward pass, what do we do? We do the gradient descent, but we need to get the gradients first for the backward pass. So now gradient with respect to W. So we call it dW, gradient of the loss function with respect to W. that one is uh, okay. Let's say gradient of the loss function with respect to d y predicted y value. So because it is a square function, I will show you this in little more detail. This is the loss square, the gradient of a square of a loss function divided by this. So I think I want to get the number of training examples. NTR, number of training, and train. This one, and train, I hope it is correct. Let's get that here. Then so I can use images. How many images are there? Okay, and train. So therefore, I can now use that here. Okay. How many are there? And then, yeah, and then here, rather than using this, I can divide this by, no, I think much more clearer now. Just averaging the mm, derivative. So this is the derivative of a square function, right? If you square it, you can get, you see that you get 2, right? So y. So dy pred, then dw. Uh, so that is the derivative of this function with respect to w. So x train and dy predict. So I will explain that later in more detail. Because I am not concentrating on the sizes, I will delete them. Maybe they are correct. Yes, it is correct. And then dy predict is db is this. Okay, now we can update the weights. Update the weight. W is this one, and D is this one. Okay, so then we can print. We can print the epoch, the batch, and the loss, and loss we can print that we can print. Now we can print the loss history, plot the loss history. Yeah, we will worry about those. I hope they are correct. Yeah, it is not required. Okay, let me check which things are generally okay. So maybe there is a size problem, so it will show up, I think. So this is, you can see, manual gradient descent. Okay, there's a problem here. So I is not accepted. Actually, I want to just loss epoch-wise loss. Dimension mismatch. Okay. Okay, let me check this. I have written report at home. I made a mistake in the dimensions, images, data. Number of training images, images dot size. Let me print that. Number of images that I'm choosing for each batch must be 50. That's what I'm saying. So 50, that's correct. About done there. The train is that, and X train. I'm flattening to this, and X train is okay. Uh, this is the problem. Okay. Okay, it is generally okay. So loss is this. Accuracies I didn't uh, print. So it will go. So for the accuracies, I will write a function now. Um, Calculate the accuracy on the training set, right? Training set. To do that with torch, no grad. So okay, I'll hit tab and explain this maybe. So you get the number of training examples. Cannot explain that. I will type it. Correct is zero, correct one, correct, and the total is zero. So um, for data in train loader, I get the images and labels, and then in train size and the view. That's okay. And you predict, and then you get the correct value by use argmax, correct class, and then if predict that label is equal to the actual label, I increase the number of correct ones. So it's okay. So now we can print accuracy on the training set is that much, correct divided by total. And you can do the same for the calculate accuracy on the test set. It will be the same thing. So hopefully it will do the same thing. Yeah. Okay. So that will plotted. So I will have 10 epochs now and run this. But you can see these are all manual gradient computations. I will explain the gradient computation equations after it. The loss should reduce. This is the first epoch. That means all the 50,000 images have been sent to the network. The loss is, you can see, slightly reducing. Okay, until then, I will explain this gradient computation step, how this was done. Okay. Before that, we had to remember how we computed the loss, right? Loss was computed as this one, right? As like this. That's the forward pass. Or we can understand by writing a few equations. So you can see y predicted. Uh, so I will just write y pred this variable. Okay, is, as you can see, uh, x times w plus b. Okay, plus b. So from this I can write that derivative of y pred with respect to w. So remember, when you write this, actually we are not computing the derivative, we are computing the partial derivative, right? All others are constant. All others are constant. Uh, Let me probably write that. So to make my life easy, shall I use a symbol for y predicted? So I will just write yp for that and see, okay, right? Yp. That's what I'm writing, no? Yp. So partial derivative of yp with respect to w, then all others are constants. Remember, when you get the partial derivative, you can see x is only multiplying. Then partial derivative of yp with respect to b is 1. Multiply of b is 1. All others are constants. So when you do partial derivative, then we have the loss function. I will call it L. Loss is equal to yp minus yt ground truth. Okay, so that is my yt squared, and it's a mean value, no? So you have to sum that and divide by the number of training examples in that batch. In this case, our n was 50. Because we took a batch of 50. So now what I want is the partial derivative of loss function with respect to w. But I cannot do that. But I can do partial derivative of L with respect to yp. What is that? So this is the derivative. This is a square. Square means you get 2. Of course, for each of them you have to compute that. So therefore, the summation will remain. And you know that if you differentiate the derivative, you get 1, right? So remember, d by dx, x n is nxn, nxn minus 1. So that means d by dx x squared is 2x. So whatever inside we have to write that. That's it. In this case, our yp minus yt is our x. Yp minus yt, and of course you have to divide it by n. But what is we don't want this. What we want is partial derivative of L with respect to W. So how do you get that? That's chain rule, right? Chain rule. So if you this is the loss, and the loss you get UYP and the yp depends on w. That's the computational graph, right? So therefore, hey, so this is like a partial derivative of L with respect to yp. This is very easy, okay? These are very few. These are things that you did when you learned the derivative. Yp times partial derivative of yp with respect to w. So you were tempted to cut this, but you know it's wrong, right? So you can see that this partial derivative with respect to yp is this quantity, and partial derivative of yp with respect to w is x. So you have to take this one and multiply that by x. That's what you need to do. Uh, okay, so let's see whether that is what the code we have. Okay, I have the code. So that is the code we have written. So you can see twice y pred minus y train divided by n train. Okay, then x train, okay, transpose times multiplied by dy pred. Dy pred. So dy pred is something that we calculated above, right? So yeah, so you can see I will write that here. So this is our dy pred. So this the notation that we use to easily identify them. So this is called dy pred. dy p. That's my dy p. To easily identify them, we use these symbols. Okay, so you can see this is dy p we have, dy pred, and we multiplied that by x. Can you see that? For b, it's dy pred times the sum, right? So partial derivative of L with respect to b is dy pred, partial derivative with respect to yp times partial derivative of yp with respect to b. Yp with respect to b is actually 1. So this one is 1. And then we just have that formula. So you can see these formulas are correct. So that's all we did actually. Yeah. So let's go back to our VS Code and see whether it has run. So you can see it has run. So our accuracy on the training set is 85. Accuracy on the test training set is that, but accuracy on the test set we have not printed. So, oh my goodness. So what I will waste computational time. So 86%. So these are not very correct. They should be lower than that, but due to some reason it happened like that. That's okay. So this is quite good. I will send this code to you. Training, the testing set. Yeah, should have printed that over there. So this is a code. So I'll put that in your chat. Is it too long for the chat? Yeah, total thing came. So you can run this and see. Mm. I hope you got a very good understanding about how we did the linear classifier. Of course, we use PyTorch variables, but we did not use AutoCAD, and manually computed the gradients, and then got this. Any questions about this? Please don't hesitate to ask the question. Okay, then. So I'll give you a few minutes to do this. So let me ask if anyone needs time. Time to do the coding. Okay, that means you're okay. Well, we will go back to the slides. Okay, so briefly about interpreting a linear classifier. So first of all, this is the algebraic point of view. We can have um, point of view like you take this image and you take the W's and reshape them to the size of the image. You can see that these four numbers you reshape to the size of the image. Remember, these are large matrices, okay? We are just representing using four numbers, but it is 784 dimensional for the MNIST. So you can see it is like template matching. We are trying to see this, whether this 56 matches with this, whether this one matches with this, and so on, right? And then of course adding the bias and get. So this is like the template matching approach. So this is the visual viewpoint. So because of this reason, after getting these W rows, and if you reshape them to the size of an image, for the car row, you will see a car. For the dog row, you will see some kind of dog. For the horse row, you will see some kind of a horse, the horse facing this way and that way, because those were the training examples. Because we learned those templates or the rows of the matrix using data. Yeah. So linear classes has no template per category. One template per category, a single template cannot capture the multiple modes of data. So therefore, if you have two horses facing left and right, they will be in one template. Okay. So let's interpret this more in the geometric viewpoint. These slides are from Justin Johnson. So let's think about the classifier score and take one pixel here. We have many pixels, but if you take just one pixel, depending on the pixel value, in this range, the pixel value is in this range, the ship score is high. If it is in this range, cat score is high. If it is in this range, car score is high. So if you take 2 pixels, now you cannot draw it like that. It's a function that is coming out of the paper. You can see the car score will increase this way, and this is a level of that function, level that we call. So the geometric interpretation is like this if you take 2 pixels. But you will see we have 784 pixels, so it's a very high dimensional picture. But in 2 dimensions, if you just take 2 pixels, the picture is like this hyperplane carving up a high dimensional space. Yeah. So, but these are all linear classifiers, Wx plus B. There are hard places for that. For example, if you take class 1, first and third quadrant, and class 2, these quadrants, linear classifiers cannot classify them. This is another thing. So this is class 2 and this is class 1, right? This is not possible. And class 1, class 2, and this class 1, that's also not possible for this linear classifiers because they cannot draw boundaries like this, but because they are just planes, right? Yeah. So we saw this, the algebraic point of view, and we need the coding also, visual point of view, I just explained, and geometric point of view, I briefly explained you. Okay. Now let's think about this four function further. So now this is, we are talking about this CFA10 data set. I made a mistake here. I put TRUC, airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. That's what you have. in this data set, these are the 10 classes. So maybe if you take a cat image, hopefully the cat score should be high, right? If you take the ship image, hopefully the ship image score should be high. So this is wrong. Hopefully the airplane score should be high. So that is what we should get from this. Given W, we can compute the class scores for an image X. But how can we actually choose a good W? So we use a loss function to quantify how good the value of W is, and we find W that minimizes the loss function through gradient descent. So what is that quantity that we use to say how good the W is? We get the square error between the predicted label and the actual label, right? So you can see this is a reasonable thing that we did. Okay, so W will change. Okay. So what is a good loss function? A loss function tells how good our current classifier is. So low loss, it is a good classifier. If it is high loss, it's a bad classifier. So something is called the objective function, cost function, this, that, and so on. So many negative loss functions, sometimes called reward function, profit function, utility function, fitness function, but they all be the same thing. So given a data set of examples, so these are, as you know, images, and these are the labels. X is I is an image and Y is an integer label. We usually convert them to one hot as we did in the code. Loss for a single example is you compute the score function and compute the difference of that between the return of that score function and the actual label yi. Loss of the data set, we have to divide by the number of data points that we are considering for the batch at that time, right? Divided by n. So all these things we did in the code. So let's look at some of these things, these loss functions. First one is cross entropy loss for the multinomial logistic regression. So we want to interpret the row classifier score as probabilities. So let's say if we get a score like that, S is equal to fxiw, we have the so-called softmax function. This is for a particular image xi. Uh, given that image, the probability of class being k. Class cat, dog, truck, that class being k class. So what we do is we raise sk to the power of e to the power of sk divided by all other e to the powers of all the classes, across all the classes. So this is a different approximation to the max function. So this is a sort of a smoothing. So these sum up to 1. So they can be interpreted as probabilities. So as a loss, we get the negative loss of the correct class, negative log value of the correct class. So we can take an example and see how this is done. Okay. So now let's take this the cat image. Okay. So the airplane score turned out to be 5.1. Cat score is 3.2. Ship score is minus 1.7. Unnormalized log probabilities. We call them logics. Then what do you do with them? We raise all of them to e to the power. Mm, So probabilities must be greater than 0. That's why you do that. These are unnormalized probabilities. So e to the power of 5.1 is 164. E to the power of 3.2 is 24.5. E to the power of that one is this one. Yeah. So then they all become probabilities. Then what we do is normalize. We divide it by this sum here, this one, and then they all are probabilities. So what is the cat score now? Cat score is 0.13. So it is sort of saying it's a airplane because it has not been trained. Probabilities must sum to 1. These are probabilities. So what is the loss? We have to pick the this um, probability of the correct class. Probability of the correct class is 0.13. That we have to pick, and we put negative log for that. See? So this one is the loss. Negative log 0.13. That turns out to be 2.04. Yeah. So if this number is close to 1, what is log 1? Log 1. log 10 1, it's 0. Log 1 is 0. If any number less than 1, like if you take 0.13, for example, minus log that 1. That is, I think this is not log 10, this is ln, right? This is ln. So 0.13 log 2.04. So let me um, uh, tell that again. This is ln, natural logarithm, ln. So if this value, when it is close to 1, it is very small. When it is close to 0, it is very large. So you can see this loss tries to increase the probability of the correct class. And it is doing what we want. Any questions about the cross entropy loss? Okay, I hope it is okay. Maximum likelihood estimation, this is choose ways to maximize the likelihood of the observed data. So it is you can compare it with the true probabilities using the Kullback-Leibler divergence also, but we will not go into that. Cross entropies and so on. Okay. Okay. What is the minimum and maximum possible values of loss? What is the baseline loss before training? Minimum, if the model assigns 1 to the correct class, that is 1, minimum loss is 0. Maximum, if the model assigns probability 0 to the correct class, then the minimum value, this is the infinity, this becomes infinity. Loss becomes very large. Special case, uniform prediction. Therefore, all the classes you predict 1.1, 0.1, 0.1, 0.1, 0.1. So when you add all 0.1s, you get 1. Special case, uniform prediction. If the model is completely uncertain, predicts uniformly distribution over C classes, probability is 1 over C, like 1 over 10. L is log 1 over C. This is log C. So for C equals 10, log 10 is 2.3. 2.3. So this is, if it is happening, you can see it's predicting randomly. So 2.3 is an important number that you should think about. Okay. I hope that is clear. Okay, now let's look at the multi-class SVM loss. This is also an important loss people use. The score of the correct class should be higher than all the other scores by a margin 1. Okay. So now let me explain that. So given an example xi, yi, where xi is the image and yi is the label, let s be the score. Okay. So we, as usual, we compute the score. Now what we want is this score should be 1 higher than the maximum score of all other classes that you get. Okay. Now assume that this is the highest score among all other classes. Okay, this is the maximum. So if the score of this particular example is higher than this margin is usually equal to 1, we say no loss, 0. Loss is 0. But if it is less than that margin, we infer loss proportional to that. But proportional to Sj minus Syi plus 1. So you can see score of the correct class must be at least 1 more than the highest score among all other classes. If that is the case, our loss is 0. Otherwise, our loss is Sj minus Si plus 1, and we maximize that over J. Okay. So let's so you can see this is this we call the margin, and this summation is over all classes except the correct class. Yeah. Okay. Now we can in if the score of the correct class is 1 higher than other classes, we incur a loss of 0. Okay. We can take an example and see. So now you can see for the airplane, assume that they assign the classifier assigned score 4.9, for the cat 1.3, for the ship 2. So here the correct class is 4.9 airplane, right? So for this, the correct class is the cat image, no cat. For this, it's a ship. The correct class is third class ship. So score has been assigned as minus 3.1. So we don't know why those scores were assigned. I randomly took those numbers. So now let's apply this one. For each of the examples, we have to apply this. What do you do this? We compute Sj minus Syi. So for this case, we have considering first. So this is in this case my Syi, right? This is my Syi. Others are the Sjs. We have others, these are the Sjs. Yeah, okay, now let's compute that. So we have to get the maximum value between 0 and 1.3 minus 4.9 plus 1, and 2 minus 4.9 plus 1. So you can see that for each of these, we do the computation for each of the other classes. Of course, this 4.9 is this one, right? So maximum between 0 and minus 2.6, maximum between 0 and minus 1.9, you get 0. Why do you get 0? Because that has been correctly classified right now. Okay. For the other one, can you briefly do it? Quickly do it and tell me the answer for the cat image. What is the SVM loss? Can you do a brief computation for the cat image? I hope you did that. So now you can see the maximum between 0 and okay. For the cat image, the correct score is 3.2. So that 3.2. Welcome back. I apologize for the network problem. I'm at the university, but network got disconnected. I'm connected to the phone. Oh. We did this computation, and for this also cat class, also cat image, also this is the loss, and for the ship also this is the loss. So we have to add all of them together. Loss over the data set will be this much. Uh, so you can see it encourages the correct classes loss to be larger. So some questions, what happens if the airplane score changes a little? So in this case, so airplane score changes a little, it does not matter because it's much more higher than the highest loss, highest other class loss. It's two, no, much more higher than that, so does not matter. What is the minimum and maximum possible losses? Okay, we'll do this. Minimum loss is 0, maximum loss is infinity when the score of the correct class is very, very low. So if the scores were random, what loss would you expect? Loss is C minus 1, 1 times C minus 1, 1 for the margin. So if the losses are random. You can think about these things. I will do not go through all of them. So briefly think about this, whether these are correct. So if you think about the cross entropy loss versus SVM loss, what is cross entropy loss? What is SVM loss? So I think you now you know these things. So for this case, I think you can compute that cross entropy loss is greater than 0. SVM loss is 0. So cross entropy loss, what happens to each loss if we slightly change the scores of the last data point? Cross entropy loss will change, SVM loss will stay the same. Cross entropy loss will decrease, SVM loss will still be 0. If the loss, the third question, what happens to each loss if we double the score of the correct class from 10 to 20? So you can see cross entropy loss tries to keep on increasing the correct classes score, even if it is being correctly classified. So SVM loss is not like that. Yeah. So please study them briefly. These are important concepts. Yeah. Okay. Now let's move to the convolutional neural networks part. Next slide set. So in the previous one, we studied about the gradient descent, and we did gradient descent examples for a one-dimensional function and MNIST data. And I showed you how to do it manually by computing the gradient, as well as how to use AutoCAD to do the gradient computation. Hopefully, we will have enough time to do an example to do a little bit of a convolutional neural network using PyTorch in this one. Okay. Now linear classifier, I think you are very familiar. We will not go through that now. And the perceptron is a linear classifier. So WX plus B. There's nothing much to think about here. Then people put hidden layers. And people use these nonlinearities. And if you don't have a nonlinearity, then the hidden layers weights can be just combined and considered as one weight matrix, and that is still a linear classifier. That's why we need this nonlinearities. If we add nonlinearities, we can learn a continuous boundary. So even this max, that means the ReLU, this max is called the ReLU, we will see that later. It's a sufficiently good nonlinearity. So we can think about the first layer as a bank of templates, second layer as a recombination of templates structure. So these are these activation functions or nonlinearities. People kept on using sigmoid. Now people and hyperbolic tangent, people don't use it anymore. What people use is the ReLU function, max t, max 0t. So when the score is less than 0, 0 is higher than -1. For example, this is -1. So 0 is higher than -1, so you get 0. But if the loss is like 5, and you get that's maximum, you get the loss as a 5. So this is that one, and then leaky value and so on, they are there. Okay. So multi-layer neural network is like that. So you have all the input nodes. Um, if you take one node in this layer, all of them are connected to that. So we call them densely connected networks also. Fully connected networks, fully connected. And if you take a node here, all the inputs are responsible for computing its value, right? That's why what these lines mean. Okay. And we looked at gradient descent. So this is the familiar gradient descent equation. Then you can see this is the learning rate, and this is the loss with respect to W. Yeah. So sometimes you have this regularization also. This is what we considered in our linear classifier example that we did. So find the network weights to minimize the training error between true and estimated labels of training example. So uh, I hope this is familiar to you. So this is the true label, and this is the predicted one, right? Predicted one. Yeah, this prediction is a function of W. That's what this shows. And the gradient descent. Backpropagation means what? Gradients are computed in the direction from output to the input layers and combined using the so-called chain rule. Stochastic gradient descent means compute the weight update with respect to a small batch of examples. That's what we did. We took a batch of 50, and at a time cycle through the training examples in random order in multiple epochs. So that is exactly what we did when we did the linear classifier for the MNIST dataset. And these things did so drastic change in year 2012 in the so-called ImageNet large-scale visual recognition challenge with the AlexNet. So people were making so-called top 5 error about 20 more than 25%, and this decreased by a very large margin. These kind of things do not happen in computer vision. That's when the world was taken by surprise by this contribution of Alex Krzyzewski, Jasus Skever, and Professor Jeffrey Hinton, who eventually won the Nobel Prize. Okay. So this is that AlexNet is a convolutional neural network. So let's study what these convolutions mean. We have already studied what convolution in our very early lessons, but it is the same thing, but I will show you again now. So we have an image, and we have a convolution kernel called, this is the output, this is the convolution kernel G. So it is 1 over 9 and all 1. So you can see each entry in these places is actually 1 over 9. So what you do is we place that convolution kernel over here at the center and compute the value of the center by multiplying the underlying numbers in the image with these weights. So all the underlying image numbers are zeros here. You multiply with zeros and you get 0 there. But when you move the kernel to the next location, now this is the new center, you move by 1 pixel, and then there is a 90 here. So 1 over 9 times 90 is 10, and that's all the summation you get, or 10 there. So you move to the next one. So you have 90 divided by 9 here, 90 divided by 9 here. So that is 10 plus 10, 20. Here you get 30, here you get 30, and so on, right? You can see here you get 1, 2, 3, 4, 5, you get 50, and so on. So this is how you compute the convolution. But remember, I'm showing you for a grayscale image. But if you have a color image, you will have uh, such a convolution kernel for all the planes. So one thing is this convolution kernel extreme locations are these, right? You can keep it here, keep it there, keep it there, keep it there. So all these are possible centers, right? All these are possible centers, but beyond that, it is not possible to keep. So therefore, as a result, these you cannot compute values for these pixels, for these pixels, for these pixels, and these pixels. So this is dependent on the size of this uh, convolution kernel. So if it is a 3 by 3 kernel, 1 pixel from all around will be uncomputable. If it is a 5 by 5 kernel, all around you will lose 2 pixels. If you want to get values for those, you do something called padding, which we will look at later. Okay. So now let's look at from fully connected to convolutional neural network. So let's take this as an image. To compute one cell in the next layer, so let's take one cell here, this one node, and consider that as this one node. All the input pixels will contribute. You can see that all of them will contribute. Now, to compute this, all the pixels will also contribute. So, but if you take a convolutional neural network, it is different. Now, this is an image. Its height is, okay, width is 32, height is 32. Depth is 3, that means it's a color image. So, we keep a convolutional kernel like so, and that kernel's spatial height is 5, spatial width is 5, and its depth or the number of channels is 3. Can you see that? Because the image has depth 3. So therefore, to compute this output number or out that cell, you have to do a 3 times 5 times 5 computations. And it's a 75 dimensional dot product. And of course, we have to do the bias also at, yeah. So that is one convolutional neural kernel. So there is one kernel, and then these weights of that kernel, 75 weights are learned. And then due to that running of that one kernel, you get feature map. But if you run more than one kernel, maybe you run 64 of them, you will get a feature map of 64 depth or 64 channels. That means if you run 64 convolutions. Okay. Now, in the next layer, remember now if it is 64, the convolution kernel's depth will be 64. Of course, its spatial dimensions are 5 by 5. So this is how we run convolutions to compute that cell. So how many computations? 64 times 5 by 5 computations, multiplication operations have to be done. Okay, now let's look at this in slightly more detail. Consider a 32 by 32 image, a color image. That's why the number of channels is 3. So let's consider that we have 6 filters, 6 convolution kernels. What is the size of each convolution kernel? 3 times 5 times 5 times 5. Uh, and we have to bias vector also. So we run this convolution kernel here, and you will get one feature map. And that is 28 by 28. Why is it 28 by 28? Because we have 5 by 5 convolution kernels. You only lose 2 pixels from the top, 2 from the right, 2 from left, 2 from bottom. That's why you get 28 by 28. If you have any question, please do not hesitate to ask or type in the chat box as usual. So another convolution kernel you can see, another one. So then you get another feature map. Then another one, another feature map, another one. And how many convolution kernels are we considering? 6. 5, 6. So you can see the output structure will have 6 feature maps. So it has 6 channels because of this reason. So if you run 6 convolution kernels, it will have 6 channels. If you run 10 convolution kernels, it will have 10. I hope that is clear. So this is a 28 by 28 grid. At each point, you can consider that it has a 6-dimensional vector. Also, otherwise, you can consider there's a stack of activations to get a 6 times 28 output image. It's not an image, it's a tensor. Now let's consider a batch of 4 images. We consider not only one image, but 4 images. So last time in our linear classifier also, we consider a batch of 50 images. If you have each image will generate a convolutional feature map of 6 channels. Next image will also generate 6 channels, 6 channels, and 6 channels. This is the output size of the output structure that you get output tensor for that whole batch. 4 times 6 times 28 times 28. I hope that is clear to you. So if you put symbols for this, Cn is the number of channels for color images is 3 for the early. So H and W is the size of the image, and N images. Yeah, N images. If that is the case, and if your convolution kernel's height is kh, so we usually 5 or 3, and width is kw, and the input number of channels is Cin, maybe if you these 3 for the early first convolution layer. C out, we consider that as 6 earlier. So you can see the output tensor size is this one. H prime and W prime we have to compute. Yeah. So when you ran this convolution kernel in this so-called AlexNet, that are two GPUs, the top GPU and bottom GPU, and you saw them as images, those kernels, they turned out to be, they ran 11 by 11 kernel. They turned out to be lines oriented in different directions and color patches. And people were very happy to see that. In the linear classifier, we saw this, right? Yeah. Okay. So when you think about this process again, so you take a convolution kernel. So we have drawn that using this pattern. You run it throughout the whole image, and then you get a feature map. You run another convolution kernel, we get another feature map. But these convolution kernels are learned uh, using gradient descent, right? So what we have is the input image, and then we will have convolution, learn convolution, and then we apply nonlinearity, and then we will have so-called spatial pooling, and then we have a feature map. So we will look at the nonlinearity now. This nonlinearity is the usual ReLU nonlinearity. We learned that a few minutes ago. So if the value is greater than 0, it is the same value. If it is less than 0, you put 0 there. And spatial pooling means you take some window and take the maximum value. It's a size reduction operation. Yeah. We will see this exactly later. And then we have these three maps. So if you take that AlexNet, it turned out to be conpool, 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 five of them, and then three densely connected layers or fully connected layers. Yeah. So now let's study about this padding operation. So if you run a 3 by 3 resolution kernel, so this is 3 by 3 kernel, so you know that you are going to lose this one pixel from all around, right? So if if your input is 10 by 10, you run a 3 by 3 convolutional filter, you will have an output of 8 by 8. How much do you lose? You lose, if these three k minus 1 many pixels you lose. So output size will be w minus k plus 1. Yeah. So that is what you need to remember. So therefore, we have to pad if you want to get the same size. So if his input is 10 by 10 and filter size is 3 by 3, output will be 8 by 8. No? So in general, input is w by w, filter is k, output size will be w minus k plus 1. So if you add a pad in, then of course the output size will become large. So a good choice is k minus 1 divided by 2. When you pad like that for a 3 by 3 convolution kernel, your padding size p will be 1. In this case, right, you can write k minus 3 minus 1 divided by 2. For a 5 by 5 filter, how much should you pad to keep the same size? P equals 2, 7 by 7, 3, and so makes output have the same size as the input. And of course, the receptive field is some concept. Now, if you are using k equals 3, that means 3 by 3 convolution kernel. The cell here in the Lth layer is produced by a 3 by 3 spatial extent of the layer L minus 1. And if you take this one, that would have been produced by a 3 by 3 pixel extent in the previous layer. And if you take this one, that would have been produced due to this one. So now you can see this is a 3 by 3 area. We call it a receptive field. This is a 5 by 5 receptive field now. If you go further, it will be a 7 by 7 receptive field. So if you generalize, each successive convolution adds k minus 1 to the receptive field with L layers. The receptive field size is 1 plus L times k minus 1. So receptive field grows linearly with the number of layers. So that means if you take the cell here, the output will have been generated by a 7 by 7 grid from there. So that's why if your input images object size is large, you need to have large number of layers. Yeah, that's why you need to. So this is round sampling mechanism content. Okay, now let's talk about the stride also. Stride means by how many pixels does this kernel move? We thought that it just moves by 1. So why should it? It can move by s pixels, right? So here let's consider s equals 2. It's moving by 2 now. Okay, so watch this. So now you see it is moving by 2. Again, it is moving by 2. So as a result, your output feature map size drastically reduces. Now it's moving by 2, right? And so on. So if your input size is 9 by 9, field is uh, 5 by 5, side is 2, output size will be 3 by 3. So how do we get that? W minus K plus 2P, that's padding. Because it is moving by S, moving by 2, you have to divide by S. So that's the formula now with the stride S. So this is something that you need to remember. Okay. So then there are 1 by 1 convolutions also. Now here you can see this is a sort of a 5 by 5 convolution. But if you make it 1 by 1, it's like this, right? So 1 by 1 convolutions, although you call it 1 by 1, remember the depth is there. The convolution spans the whole depth of the whole number of channels, and it will be a channel-wise addition, channel-wise weighted addition. Yeah. Okay, let's do this brief computation to understand whether these numbers are okay. If an input image is of size 32 by 32 grayscale, and there are 6 filters of dimension 5 by 5 uh, filters, and if the stride is 1, padding is 2, compute the output feature map size. Number of learnable parameters. Number of learnable parameters if the image were color image. Number of multiply operations for a color image. So first, let's do that. If the input is a 32 by grayscale image, there are 6 filters of dimension 5 by 5, and the stride is 1. The grayscale image now. So if you take the image, it's a grayscale image. So number of channels, so the depth is 1, right? That's a grayscale image. So it is size is 32 by 32, right? And the stride is 1, padding is 2. Compute the number of output feature map size. What will happen? So what is the formula for this? So W minus K plus 2P divided by S plus 1. W minus K plus 2P divided by 2 divided by S plus 1. That will be the size of the output feature map. So you can see W is 32 and the kernel size is 5 and stride is 1, padding is 2, that means 2, 4. The stride is 1 plus 1. What do you get? 38 minus 4. Yeah, 32, right? 32 by your feature web size will be 32 by 32. Um, Output feature web size is 32 by 32. Number of learnable parameters, how do you compute that? So there are 6 filters and 5 by 5 convolution. So each convolution is 1 times 5 by 5, right? Because number of channels is 1, and you have 6 of them, right? 6 of them. And then you have bias also, so I have plus 6. So 156, right? 156. Number of learnable parameters if the image were a color image. Okay. So if the image were a color image, the number of channels will become 3. 3 times 5 times 5, right? Number of convolution filters is 6. And the bias is 6. 456. Then final one is number of multiply add operations for a color image. Multiply add operations for a color image. So we have to consider the output structure. Our output structure will be, structure size will be there are 6 and 32 by 32, right? 32 by 32 times 6. That's the output structure. So to compute each of these cells, we need to spend 450, that many computations. So 3 times 5 times 5, that many computations for each of them, each of the cells. So how many cells are there? 32 times 32 times 6. These are the number of multiplied operations roughly. Okay, here is the answer. So I will clear all the slides. So yeah. Oh, okay. These are correct, right? Yeah. I hope that these are okay for you. Any questions about this? Okay. So here is a summary of these things. You can read about it. I think now these formulas are familiar to you. And these are typical values that people usually use. So k equals 3, padding 1, stride 1. That's the usual setting that people do. Okay, about max pooling. So now this is a output feature map, and then you go to max pool, you take this window and pick the maximum value. That's all. That's all, max pool. So for this 8, for this 3, for this 4. So you can see the stride is 2. The 2 by 2 window is moving by 2. That's that. Then you downsample by 2. So max pooling, summary. So h minus k divided by stride plus 1. Yeah, that's so this is typical. K2 S2 is typical, but in the AlexNet they use k equals 3. So okay, now in regard to the existing architectures, we will look at the Lenet 5 architecture. Yeah, given the time, I don't think we'll be able to code it, but I want to code this Lenet 5 and show. I will show that next time, but I will describe it today. Hmm. Uh, Now input is the 32 by 32 grayscale images. Now you can see it has convolution layer, subsampling. Consider that as max pooling. That actually there is average pooling. Another convolution layer, subsampling, a fully connected layer, and Gaussian connections. I think that's all. Now you can see the size has reduced from 32 by 32 to 28 by 28. What would have been the convolution kernel K size? We can see it must have been a 5 by 5 convolution. 5 by 5. What is the kernel 5 by 5 con? So what is the actual size of the kernel? 1 times 5 times 5. Right? Why do we write 1? Because in the previous layer, the number of channels is 1 because it is a grayscale image. Okay. Now what has happened here? Subsampling, it has become 14 by 14. Of course, because of this, we know that side is 2. Side is 2. That's why the subsampling happened. Then another convolution. So you can see number of channels has become 16. 16 kernels must have been there. So here 6 kernels, 16 kernels here. And the size has become from 14 by 14, 10 by 10. So that means, therefore, we know that it's all again 5 by 5 convex. Yeah. 5 by 5 convolution. So because the input number of channels is 16, each convolution kernel would have size 6 times 5 by 5. Yes. Then again, the subsampling layer, you can see from 10 by 10, it has become 5 by 5. Therefore, stride must have been 2. And this structure size is 16 times 5 by 5, that means 400. So therefore, this fully connected layer is a 400 to 120 layer. 400 to 120. So if you consider the biases also, that's the number of operations, and then 120, we have to add as the bias. This fully connected layer, 120 to 84, 120 to 84. So because of the biases, we add another 84. This Gaussian connection, it's a fully connected layer, 84 to 10. And we can consider the biases and 10. So I'm writing the number of learnable parameters for the fully connected layers. For the convolution kernels, what is the number of learnable parameters here? 6 convolution kernels of um, um, 1 times 5 times 5, and 6 of them are there, and 6 biases. So that means 156. Okay. For this convolution layer, so each kernel size is 6 times 5 times 5. And 16 of them are there. And bias is 16. How many parameters? So let's do a brief calculation. Hmm. 6 times 5 times 5 times 16. 2460 parameters. So how many here? 400 times 120 plus 120. 48,120. 48,120. This one, 128. 120, I'm sorry, 120 times 84 plus 84, 10,164. This one we can compute without that. 840 times 10, 850. 840 plus 10, 850. So if you want to compute the total number of learnable parameters, sorry, total number of learnable parameters, we have to add this number, this number, this number, this number, and this number. We can do that quickly. 156 plus 2,416 plus 48,120 plus 10,164 plus 850. So 61,706. I hope this is correct. 61,706 learnable parameters. Total number of learnable parameters. So not too much. It's very small amount of learnable parameters. So they used average pooling, sigmoid row, hyperbolic tangent, and linearity, fully connected layers at the end, trained on MNIST-digit dataset with 60,000 training examples. Yeah, this is what Lynette meant. Lynette Pie meant. So maybe we have time to code. So if you are okay, I will code this. Uh, but I will be, yeah, that's okay. Yes. go to your folder. This is what we have been doing. Let it find like structure. Yeah, a little bit of classes. A class, we had to write a class. So I will get started like torch, import torch. Let's see how fast I can do this. Import torch.nn as nn, neural network, and optimizer, and torch vision, and then transforms, of course, and matplotlib. No, we don't need. So now we'll code the class of the Linet5 class. Lay this in honor of Anticon Linet5. It inherited from nn.module, so it knows what I'm typing. Def. Init. So what runs when you initialize one of those? Init self. Self. Yeah. Okay. And then we have to do super init also. Super dot init. That's okay. And then now this is the important part. Now first I'm going to define the first convolution layer, self dot conv1. This is very important. So what is the first convolution layer? So remember in this one, we had 5 by 5 convolutions and we had 6 of them, right? Okay. So these are two-dimensional convolutions. nn dot con2d. How many convolution layers? Input. How many input number of channels? In channel is 1, right? And then out channel is 6, and the kernel size is 5. So you can see it is exactly what we did in the slides we are writing. Then after that, we have a pooling layer. We have a pooling layer. They call it subsampling. Stride is 2. That's the important parameter. No, stride is 2, but we will be very close to this self dot self dot pool 1. nn.max pool, they use average pooling, so I will use average pooling. nn.avg pool, average pool 2d, and the kernel size is what we need to give, and the stride we have to give. Kernel size stride. Actually, they use kernel size. I don't know. Then the second convolution layer, uh, it has 16 output number of channels. Input number of channels is 6, and it is a 5 by 5 convolution layer. So that's correct. Con2 in channels is 6, out channels is 16, kernel size is 5. Then another pooling layer we had, right? Another pooling layer, that's also correct. So this is that pooling layer. Pooling layer. After that, we have to flatten it to 400, right? Flatten it to 400, then connect it to 84, connect it to 120, 84, and 10. So now the flattening part has to be done. So flattening part we can do later. So then we have the self. Actually, we are only defining the layers. Like we did not do any computation yet. A linear layer from 6 times 16 times 5 times 5 to 120. Then another linear layer, 120 to 84, another linear layer, 84 to 10. So now we have defined that. Now we have defined the forward path, f forward, self.x. So you are taking an image x, and then we are producing this, we'll use the same symbol as x, but we are taking that image and applying that to torch dot hyperbolic tangent, tan hyperbolic tangent after the first convolution layer. Remember, after the convolution, we have to apply a nonlinearity. So hyperbolic tangent is what they use. So put x into the convolution one layer and apply the hyperbolic tangent. Then the next one, x is, now we have to apply the pooling. Self pool, we have to apply the pooling, self dot pool, and we put this x into that. Next, the second convolution layer, you can see apply the convolution and apply the nonlinearity. And then as the next one, we apply the second pooling. Then we have to flatten that. Flattening is very important. Because we have to convert it to a 400 vector. That's the flattening you're doing. So taking the size and viewing it as that one. And then as the next one, x, we apply, of course, the torch dot nonlinearity tangent, hyperbolic tangent, and we put the x into the fully connected layer one. Then second fully connected layer, and finally third fully connected layer, and we return it. For the final fully connected layer, we do not apply a hyperbolic tangent function. Yeah, I hope that this network forward path definition is correct. So this is very important to relate that to what we designed on this. So see, we are hand coding the convolution neural network and we are training that. And you can see that usually we do not do that. We use trained neural networks and use their weights from the internet. But right now, this is not something that we are doing. We are hand coding. Okay. Then the transform and data part, I will directly take from the last thing that we did. So in the transformation is I'm padding with it too, because these images are 28 by 28. I want to make them 32 by 32. Batch size is 50. We save it in data. So MNIST 1. I think there's nothing much to do because MNIST is I have already downloaded that. So okay. I'm directly taking training set and test set, but actually the validation test is required. Why is it bugging me? Transform is not defined. So yeah. Okay. So now a few things to do, and then we have to run for several epochs. Before that, I had to put the network into the device, torch, device, CUDA if torch CUDA is available, else CPU. That's the device. So I have fortunately CUDA. So then model, now this model LeNet 5 to device. So we have to do that. So now LeNet 5 has been initialized, and then we have to have criterion for the loss. So cross entropy. Now you know what cross entropy means. And then we have optimizer. Optimizer, we will use Adam optimizer. So there are many optimizers. Model dot parameters, learning rate is fine. This is Adam optimizer. Is a very robust optimizer. Yeah, that's okay. Learning rate is 0.001 or something, and not something, this one. So for logging, we need some parameters, batch losses, batch losses, batch losses, number equals 10, and maybe you can have train losses. I hope I will be using this variable, train losses, and then train accuracy, train accuracies, and test accuracies. Okay, so those have been there. Now we will do the epochs, training epochs is, let's put just 5. And now for epoch in range just epoch. Okay, range epochs. Now model dot train running loss. Running loss is 0, and we have to get the data and from the train loader as we did before, and apply that to the zero the gradients, then compute the output and compute the loss, right? For data, comma labels in train loader, right? And we have to put the data in the data and labels, data to device. Device is, in my case, the GPU, labels to device, labels to device, and then optimize a zero grad. That's correct. So now it knows what I'm typing, right? Zero grad. So we have to make the gradient 0. Then we compute the output model. We put the data means the images to the model and compute the output. And the loss is outputs and labels because the criterion we have. And then you can say loss backward. And then optimize the step. We can take a step in the optimization. So gradient descent, are we writing manually? No. Now we are letting PyTorch do this. So losses, running loss, loss dot item, batch losses, append loss item. That's okay. So now we have a little bit of a uh, train train losses. So running loss divided by length of the train load. So how loss in the training, and then we can print print the epoch and the loss, average loss. Okay, these are okay. So that has to happen outside this. Okay. So yeah, for every epoch we will print that. Um, we can calculate the training accuracy. Model dot eval part. Correct. Total 0. So with torch no grad, remember now we are doing the evaluation. With no grad we have to do. We don't compute gradients here. So load the train loader, cast to the device, compute the outputs, and then you get the correct labels, you get the max, torch of max output. And then if the predicted label is equal to the actual label, we call it correct. So train accuracy, uh, like so, and the train accuracy, we can append that to the history, and then we can calculate the test accuracy, total, the same thing. Yeah, so we are loading from the test loader, you can see, right? Not from the training loader. We are loading from the test loader. Test accuracy also we can print. And then we can do some plotting. I will copy the plotting code from what I have done from home, at home. So this is it. So I hope it will run, and we will run that. And I will send you this code if it is running. Oh, there's an error. Error. Each of the superobject needs an argument. So did I miss anything? Def init super. Forgot the parenthesis. So one more error. Data size mismatch problem. Mhm. Also, correct transfer value size is 2. Transform has been applied. I think this error I might not be able to correct once. I'll use try to use AI and correct it, but if it's not possible, maybe I will write the code and email you or something. You cannot find this at once now. Load transit, transit, transform, transform the padding just two. What is it trying to correct? Oh, I have forgotten to put 45. That's the reason instead of 5. That's the problem. This is actually 400, right? I decided that. Let's see, that starts training. Because it has run one epoch, that's why it's taking time now. So now you can see it's working, right? So hopefully it'll loss will reduce and the accuracy will improve. So because we have 5 epochs, it will take a bit of a couple of minutes. But I hope it is okay. There is a quiz, I think, so please do that also. You can do it fast. And then there are two pieces. One for next, what we missed last time also. I have activated that to be done by tomorrow night, I think. These are very simple pieces. So now you can see the loss is drastically reducing. So there are training recipes. Okay, you just don't keep the learning rate the same. So learning rate schedules and all these things are there. Uh, but right now we are not discussing those. But it's good to if you compute the accuracy also, it would have been nice. But I think I forgot to write that code, accuracy of the training set and so on. So 2 or 3 minutes, in 2 or 3 minutes it will be done. Because it's a small data set and it's a reasonable network, it is working there. So if you understand this part, that's very, very good. That means you have been able to relate it to the slide that we had. And then the procedure for getting that optimized, loading the data set. And for 5 epochs we run, each of the epochs we get the train loader to give us a batch of data. Like how many data points will it give? It will give 50 of them because we have set the batch size is 50. So using the train loader and test loader, we access them. And then we get the data and images and labels we put to the device. It's a CPU or the CUDA. And then in the optimizer, we zero the gradients and we compute the model outputs. That means the predicted labels, and then we compute the loss. And then because it is computing the gradients, we just have to say loss backward to get all the gradients computed with respect to the model parameters. And then we say optimize a step. So that's all we have to do. Then all the loss computations and so on are not actually part of the training process, but they are for us. So loss is reduced. So you can see the rate of reduction is becomes smaller. So give me one minute to finally show you the. So hopefully the graph will also work. I just copied from the home example. So could we please know whether the next week will be the last lecture of the course? Could you also know if the exam includes questions from all lectures 1 to L20? So I want to do, yeah, thank you for asking that. So next week I have a problem. I have been asked to come to a school for the Hampasala for some thing. Function. So I have to go now because one of my teachers have asked. So I will try to find additional extra 2 lectures. I have to do 2 more lectures because we missed some classes. 2 more lectures within the next week. Within the next week or week after. Next Sunday there will be no class because I cannot come. So I will talk with the coordinators and explain you. Then depending on the number of slide sets that I do, it will come to the exam. So PLT is not defined, so unfortunately you cannot get the plots. But let me see whether I can get the plots also. Mm, yeah, is that the problem? So let me see if the plots are possible. Yeah, you can see the plots are possible. You can see the train accuracy is increasing, test accuracy is increasing, and it should reduce. And that's the place we should select, and we should not train further. So actually, there's some mistake. I should have done a validation using a validation set. I should not have tested it directly on the test set. So you can see the loss has reduced. It's always noisy, and the loss training loss on that's okay. So that's all we want to do for today. If you have any questions, you can say and ask. Of course, I will stay for some time until you log off. So no class next week. I will get additional time slots from the Dr. Tilini Tilaka and inform you. I had to do 2 more classes. So no class next Sunday. So I have to do 2 more classes, additional time slot. Thank you very much. Have a pleasant Sunday afternoon, everyone.
Thank you.
Thank you.